Okay, we're going to continue on here, chapter 9. So in this chapter, we mainly talked about at the beginning, I think, intermolecular forces. And remember that intermolecular forces are those forces that hold basically one molecule together with another. And really, all intermolecular forces pretty much are the same sort of interaction. It is that electrostatic attraction where basically the negative side of one molecule is going to be attracted to the positive side of another. And that ultimately is how all these intermolecular forces basically work. And there's a few different types that we talked about. On one end, you sort of have hydrogen bonding, and that is really a dipole-dipole interaction, and it's a relatively strong interaction, and it has a bond between hydrogen and some type of electronegative element like nitrogen, oxygen, and fluorine. So again, in order for it to have the ability to actually hydrogen bond, you do need to have that hydrogen that's directly attached to one of those three elements there. And because those are really electronegative type elements, or strongly electronegative, it will create a pretty good separation of charge, and that's what's going to allow it to really interact well. This is the main type of intermolecular force for polar molecules that can hydrogen bond. So obviously, if it's a polar molecule that can hydrogen bond, it's going to basically do that. And that's, again, what we see in something like water, which has that ability to do that. Sort of a broader class of interactions is dipole-dipole interactions, and dipole-dipole is the main type that we have for polar molecules that really cannot hydrogen bond. So if you have a polar molecule that cannot hydrogen bond, it's going to go with just dipole-dipole interaction. Also relatively strong, but hydrogen bond is still a little bit stronger, even though it's really a type of dipole-dipole. We also talked about ion dipole interaction, and ion dipole is basically what happens when ionic compounds dissolve in something like water, where the ions get surrounded by the polar molecule of water and really allows it to dissolve. Sort of at the other end of the spectrum is dispersion forces, and dispersion forces are really the weakest of all intermolecular forces. They are really the main type of intermolecular force that nonpolar molecules use. Now, truth be told, everybody, even polar molecules and everybody, can do a little bit of dispersion forces and interact that way. But really, that's not their main route of interaction for nonpolar molecules. This is pretty much their main way of interacting. And the way that molecules interact with both themselves and also other molecules through these intermolecular forces, they affect a lot of things that we were talking about, like solubility, like boiling points, melting points. And typically speaking, if you have a really strong intermolecular force, that guy's going to be held together pretty strongly, and that's going to translate into a higher boiling point, a higher melting point, because it's going to take a lot more energy to get those guys to break apart, which is pretty much what you're doing at those sort of transitions. And if something is held together by a much weaker intermolecular force, it will have a kind of lower boiling point, melting points, because again, they're not held together as tightly. So it doesn't take a lot of energy to get them to sort of separate apart. Um, that I think we talked about like dissolves like, and that's the idea that things that use similar intermolecular forces that they use with themselves will also work really well with others that use a same type of intermolecular force. So if you take something that's ionic and polar together, you're going to be in good shape. If you take something that's polar and polar together, you will also be in good shape. And also, if you take something that's non-polar and non-polar together, you will be in good shape. All these guys will typically be soluble in each other because everybody's using basically the same type of intermolecular forces. Only when you sort of cross over and you kind of go polar and non-polar, you're going to run into some trouble there, and it's not going to be basically soluble in each other. Again, because somebody that's polar is going to use either hydrogen bond or dipole as really their main route of interaction. And something that's nonpolar is going to try to use those dispersion forces, which, as we talked about, is basically a couple of ways you could kind of do that. You could have an instantaneous dipole, which is caused by either an ion being present or a polar molecule being present that temporarily gives this nonpolar molecule some charge so it could interact. You also could have what we talked about, polarizability, which is the ability of the electrons in a molecule basically to end up all kind of in the same location, if you will. And what that will do again is create a temporary separation of charge in a nonpolar molecule that allows it to interact. Again, because those are temporary, they kind of break apart, come back together, and it's not a great interaction. And that is really the main difference between when you think about polar molecules and nonpolar molecules, how they're able to interact and why, for example, hydrogen bond and dipole is a much stronger intermolecular force. And that is because if you have a polar molecule, no matter what you do to it, it always will have that separation of charge. So there will always be a positive side of that molecule. There will always be a negative side to that polar molecule, which means right out of the gate, it's good to go to start interacting, start bonding. And that's different than, say, a nonpolar molecule who right out of the gate is pretty much neutral. It doesn't have a positive side. It doesn't have a negative side. It has to rely upon something happening for it to temporarily gain that positive negative side. And that's why it's, much weaker force. That sort of interaction has to be sort of made before it can actually do the intermolecular forces and start interacting. So we talked about that there. Any questions on that stuff there? Also, we talked about the idea that dispersion forces, although they are weak, there is sort of a different strength of that weakest force. So when comparing things that use dispersion forces, the stronger dispersion force will result for something that has more molar mass. And because it has more molar mass, I'll spit that sentence out, I think. Because it has a greater molar mass, it will probably have more atoms, and more atoms means it has more electrons, and greater opportunity for those sort of distortion of those electrons to occur. Also gives it a lot more places for things to interact at, more sites on the molecule for it to interact. So if you're comparing, as I talked about last time, two nonpolar molecules, you want to know which one would have like the higher boiling point or melting point, it would be the one that has the greater molar mass, even though they're both using dispersion forces. Now, if you compare any of those two, for example, use dispersion forces, something that uses hydrogen bonding is going to win all the time because that's way stronger of a force. So something that has the ability of the hydrogen bond usually will have pretty high boiling points and melting points. Any questions on any of that there? Okay. I think we left off talking about vapor pressure, if I'm not mistaken, and sort of looked at this picture here. And a reminder that vapor pressure is the pressure of the gas that's over a liquid. And at the surface of any liquid, as we talked about, you constantly have guys kind of escaping the liquid phase. And you also have slower moving sort of vapor guys that are going to come back down. So you do have this sort of always sort of things going through evaporation and things going through condensation at the surface of any liquid. And what happens is, in the case of some liquid that has a fairly strong sort of intermolecular force, so it's held together with itself pretty strongly, it's not going to allow a lot of guys to escape the liquid. So what will happen is you'll have a lot less sort of vapor molecules above the liquid, and that would translate to a lower vapor pressure. And that's different than if you had a liquid that's held together by dispersion forces super weak. You're just going to have everybody exiting the liquid pretty easily without a lot of trouble. And that would result in a lot more, obviously, vapor molecules, gas molecules above the liquid, and that would give you a higher vapor pressure in that case. Those type of liquids are what are said to be volatile, as we talked about. They just basically can go from the liquid phase to the gas phase, which is not a lot of work. Just leave it open, and that's enough for it to basically just jump out of the liquid phase and go to gas phase. Now, we could actually calculate some of the pressure relationships here that occur at different temperatures. And we can use this equation here, which is the natural log of our vapor pressure at the first temperature divided by the vapor pressure at the second temperature. This is the delta H of vaporization, and the delta H of vaporization is the heat of vaporization, as sometimes referred to. And that is really the energy required to change a substance from liquid to gas or gas back to liquid. So that is the energy required basically to do this transition, which occurs at the normal boiling point. And it is the amount of energy required to simply do that transition at that temperature. Remember that if you do this transition, it occurs at the same temperature, right? So if we're talking about, for example, water, it would be 100 degrees Celsius. At exactly 100 degrees Celsius, you have basically both phases happening at the same time. You have liquid water, you have sort of gas or steam happening at that time. Not till you get above 100 a little bit, you get fully sort of steam, not till below 100 that you do drop into liquid water. But at exactly 100 where this happens, that phase change occurs. And the energy required to do that is what's known as the heat of vaporization. By the way, for water, it's roughly like 40.6 kilojoules per mole, or about 2260 joules per gram, give or take, here. And actually, the number is the same regardless of which way you're going. It's just whether or not the process is endothermic or exothermic. If you're going from liquid to gas, you have to put energy in to do that, right? Like you're boiling some water for pasta, right? You put it in there, it starts to boil, you get steam. That is an endothermic process. It would be positive, say 40.6 kilojoules per mole. If you're doing condensation, which is removing the energy from those gas molecules to slow them down so they stick together to come back to the liquid, it would be negative because it's exothermic, kilojoules per mole. Same thing with the 2260 number, would be positive going from liquid to gas and negative going from gas back to liquid. And so that is the delta H of vaporization. R is the gas constant, but it is the energy version of the gas constant. So the R here is 8.314 joules per Kelvin per mole. These are our temperatures. Probably no surprise, should be in Kelvin, each of these guys here, and so forth. So we could take our vapor pressure here and calculate, you know, different temperatures or what the vapor pressure would be at different temperatures. So let's take a look at it here. The vapor pressure of water at 25 degrees Celsius is 23.8 torr. The heat of vaporization at water is 43.9 kilojoules per mole. Calculate the vapor pressure of water at 65. So I want you to take, well, there's the answer right there. So let's see how we get to that answer. So we could use this equation here, which is a natural log of our P1 over P2 is equal to our delta H of vaporization over R. 1 over T2 minus 1 over T1 is essentially how we get there. Now, one important thing that you do have to watch out for when you do use this equation is actually these two guys in terms of their units. So very commonly their units are kilojoules for delta H, and for R it's joules. So you got that 1,000 sort of difference between them. You just have to watch out for that. So we can call P1 23.8 torr. We can call our T1 that goes with that 25 degrees Celsius, which if we just convert to Kelvin will give us 298. We could call our P2 what we're looking for, and our T2 would be 65 plus 273 to convert it into Kelvin. So 273 plus 65, about 338. Now we also have our delta H of vaporization here, and they're going with 43.9, so we'll use that number, 43.9 kilojoules per mole. So we do have everything we need except for P2, so we could actually put it into this equation, and we'll go with the natural log of P1, which is 23.8 torr. over P2 equals, now what I'm going to do is I'm going to convert my kilojoules into joules so that I got the right units. So I'm just going to simply take my 43.9. I'm going to times it by 1,000. And what that's going to do is convert it into joules. And the reason I'm doing that again is because R is also in joules. So that way, unit-wise, everybody cancels out correctly. So you do have to watch that. You could also convert R into kilojoules and leave the delta H in kilojoules. But you do have to really do one conversion to get them to the right units. We're going to go 1 over T2, which in this case is 1 over 338 minus 1 over T1, which is 298. All right, so we have everything on the right-hand side. So I'm just going to kind of clean up the right-hand side here. So 1 divided by 338 minus 1 divided by 298. We'll times it by 43.9 times 1,000. And then divided by 8.314. And that's going to give us basically the natural log of 23.8 torr over our P2 will equal minus 2.096918. To get rid of the natural log, you need to take the E of both sides on your calculator there. That will get rid of the natural log on that side, and that will leave you, and I think I'll just go up on top so it'll be easier to see probably here. Let me just get rid of this. There we go. All right, so if we do that there, we will end up with 23.8 torr over P2 is equal to 0.122834. We're going to multiply this to that side, and we're going to divide that guy back to the other side. Yeah, so we're going to go 23.8 divided by that answer, basically. And that's going to give us a P2 that is about 194 torr, as you can see on the bottom there. Yeah. First off, any questions on the calculation here? So again, just watch out on that part right here, unit-wise, that everybody's in the same units. Otherwise, you will find yourself off by a factor of 1,000. Any questions on that? Answer does make sense if we think about it at 25 degrees Celsius, which is a lower temperature. We had a vapor pressure of 23.8. We bumped that thing up about 40 degrees, much hotter, right? That's going to allow a lot more energy. That's going to allow a lot more of those liquid molecules to escape. And we should have a greater amount of vapor molecules above the liquid. And that is what we see here in terms of the pressure. We end up with 194 torr, which is a result of the higher energy from the temperature, releasing a lot more of the gas molecules into the gas phase. And since we have more gas molecules above the liquid, we have a higher vapor pressure. Any questions on that there? Yeah. So let's talk a little bit about some of these processes here of liquids. So when a liquid is heated at a higher temperature, bubbles of water vapor start to form beneath the surface. And when these bubbles really are able to escape the surface of the liquid, that is when we really have our, say, water, for example, boiling. Before they are able to do that, what happens is we get these water vapor bubbles, but if the pressure inside the bubble is less than the sort of atmospheric pressure, they pop before they make it there. So it's not until they build up enough pressure in those bubbles that you see that they're able to actually escape the liquid at that point, which is the boiling point. Now, you might have heated water before, I assume, in your career here. And you might, well, as soon as you hit it with the fire, you might see a lot of like what some people describe as little bubbles kind of forming. And that's not really obviously your water boiling because you just hit it with the flame a second ago and you can put your finger in there and it's still cold. And what that is actually just the difference in temperature causes something like the CO2 in water to escape and be less soluble in the liquid. And what you're actually seeing is just that solubility of CO2 kind of escaping really quickly. Obviously, not to get the bigger bubbles and it's really coming to the top that you do have something that starts to bubble or boil. At lower temperatures, the pressure inside the bubble again will sort of collapse and it's not boiling. At what temperature something boils with does depend on the temperature and pressure. So if you play with pressure or temperature, you could change the boiling point and get something to boil. So if you go at a higher altitude, the boiling point would be different than, say, if you were at, say, sea level. Now, raising the pressure increases the boiling point. So one way we can see that in real life is through like a pressure cooker. And in this case, when you put that tight lid on the pressure cooker, it holds the pressure on the vapor above the water, resulting in an increased in boiling point. So you get this water vapor up here that can't really escape because of that under pressure. And again, it's going to take a lot more higher temperature for that water inside there to boil because there's a greater atmospheric pressure because of the lid basically going down on the liquid water there. And it's going to cause obviously the bubbles to burst at a much lower temperature, even a higher temperature really. So it's not until we get to a really high temperature that they'll be able to actually start to boil and obviously can cook your food a little bit differently than normal. Boiling, as odd as it sounds, is a cooling process, and boiling is actually cooled as fast as it's heated from the heat source. That's why if you ever look at a thermometer, it tops out at like 100-ish degrees or 102 degrees because technically the boiling point of water is at 100 degrees. And when it hits 100 degrees, it stays there unless you do something to make it go higher, but it pretty much will stay there. It won't go much higher. So the idea here is as you're heating from the bottom, what happens is we get these guys boiling and these guys escaping the liquid. The result of that is we are cooling out the top. So we get these fast moving water molecules that are boiling, escaping the liquid, which means they're no longer there with their energy, and it's sort of cooling the liquid from the top as they escape as you're heating it from the bottom. Now, liquid in the gas phase, I am the gas phase, the process there, as we talked about, as we go from liquid to gas, or gas back to liquid, is evaporation or vaporization. That is an endothermic process. You do have to put energy in to do that. So as we just talked about a second ago, if we did our delta H of vaporization going in this direction, it would be a positive value that you would use. And obviously condensation, which is the opposite play, where we go from gas molecules to liquid. Gas molecules are flying around with a lot of energy. They have to release that energy to slow down. And when they do, they no longer have enough energy when they hit other gas molecules to escape. And they kind of clump, if you will, and fall into the liquid out of the gas phase because they have lost some energy to do so. As I mentioned before, at the surface of any water, there is a constant exchange of molecules jumping out of the liquid and falling back in. As we talked about, I think last time, if you just had a little bit of water on the bench, it will start to evaporate because of that. It will start to evaporate and the air will blow away those guys and not allow them to come back to the liquid. And that's why it fully evaporates along the way. So as I mentioned before, as those liquid molecules escape the liquid, they take a lot of their kinetic energy with them because it has to build up enough energy to escape and go into the gas phase. The result of that is the water as a whole will lose all that energy and is essentially cooled. And when those newly sort of escaped water molecules escape the liquid, they are moving a lot slower than the air molecules because they took a lot of energy to escape. So when they get out there, they're actually moving a lot slower. So as a result, the air is actually cooled as a result of that heating process there and that boiling process, which sometimes is weird for people because they think like it's hot when you put your hand there. But again, that's all that energy sort of coming off. So water cools, the evaporation rate decreases, and we can maintain, for example, an evaporation rate if water comes in contact with a warm surface, like our skin, right? So That is why we feel cool, right? If we have water on our skin and like get out of the swimming pool or the shower and you got a lot of water on your skin, the reason you feel cold is because basically all the water is going to suck out the heat and energy from your skin to start the process of evaporation. The result of that is you feel cold because you're losing all your energy to the water that's on you, and you start to feel really cold because you have water and you're really doing a lot of evaporation at that point. That's also why we sweat, right? When we get overheated, right? In a process to put water on our skin to allow the process of it to start to evaporate and release some of that energy, right? And cool us back down. So that's really why we do those things. So evaporation is a cooling process as well. Now, when we have at the surface of water condensation and evaporation occurring, condensation occurs when we do get those slow moving water vapor molecules that collide with the surface of the liquid. Fast moving water vapor tend to bounce off one another, but when they're slow, they tend to condense and come back to liquid. That is also why condensation is, for example, a warming process. So when you're taking like a hot shower, and you get all that mirror gets all wet because the hot steam right hits the cold mirror, you get condensation. In addition, the rate of condensation is occurring, and condensation is an exothermic process, which means if you're standing in the room where you have a lot of steam and it's going through condensation, basically, you're going to pick up all that energy and you're going to feel really warm till you shut the shower. Now you got a lot of water on you, and now you're going to have the rate of evaporation occurring, and you're going to feel really cold, right? So that's what's happening with condensation. Again, because it's an exothermic process, it's actually going to release that energy. And that's why, again, when there's a lot of steam in like a room, like a steam room, a sauna, something like that, for example, as well as like when you're taking a shower and it's really warm, you are picking up all that energy as the process of condensation is occurring, and that's why you feel warm in those situations. Now, as I mentioned before, there is the heat of vaporization and the heat of condensation, and it really is the energy required, again, nothing more than to move a substance from one phase to the next, again, not changing the temperature. So when we talk about water, which is 100 degrees Celsius, where that occurs, that's the normal boiling point of water. And at 100 degrees, we could take liquid water to gas or steam and also go backwards. And that again is our delta H of vaporization that takes care of that. We are not changing the temperature, but we are changing the phase. When we actually change the temperature, but keep the same phase, you might be familiar with what equation you use. That is the specific heat equation that maybe you learned in the previous class, which they no longer teach in this class until next class they teach it. But you actually use the specific heat equation there to calculate the energy required to change the substance from one temperature to the next, but it's going to be in the same phase. Like take liquid water from 20 degrees to like liquid water at 60 degrees, right? So it's all liquid water, just changing the temperature. Q, by the way, is heat, our energy, and that's joules or calories. M is mass, which is grams. Delta T is the final temperature minus the initial temperature. And it's one of the few temperature values in chemistry that actually usually stays in degrees Celsius. It doesn't actually get converted. And the reason for that is S. Some people use S, some people use C for it, some people use SH. I don't know, it depends on who you take. That's what's known as the specific heat capacity. And that has units of joules per gram per degree Celsius or calories per gram per degree Celsius. For example, maybe if you remember this stuff, water is 4.184 joules per gram per degree Celsius or 1 calorie per gram per degree Celsius. The definition of specific heat is pretty much the units. It's the amount of energy required to change 1 gram of a substance by 1 degree Celsius. It's basically what the units are. So that is the energy. If something has a very high specific heat capacity, it takes a lot more energy to change the temperature of 1 gram of it than it does if something has a low specific heat capacity. Water, for example, has a pretty high specific heat capacity at 4.184, which is why people get nervous when the ocean water changes just slightly temperature, because the amount of energy required to do that is an enormous amount of energy just to move that much water, just that little bit of temperature. Any questions on that there? So again, as we talked about there, you feel warm in the shower because again, you get the benefit of all that condensation happening. Again, until you get to that, a rate of evaporation will outdo it when you shut it off. Less steam, more water on your skin. Now, freezing and melting also occurs at the same temperature, and that is the normal freezing point or melting point of a substance. And for water, for example, that is 0 degrees Celsius when that occurs. And melting is when we change the substance from a solid to a liquid. Basically, it gains enough energy to start moving past each other, right? In the solid state, they're just rigid. They're kind of not enough energy to move past each other, the different atoms and molecules. So as we start to heat it and melt it, they gain enough energy. They start moving past each other. Our solid now is more fluid because molecules and stuff can move past each other and they pour. Now, freezing is the opposite. When we release all that energy, things stop moving, and they kind of lock themselves into place because they no longer have enough energy to keep moving past each other. So they just kind of lock each other into place. At this temperature, at 0 degrees Celsius, exactly at 0 degrees Celsius, you do have both phases happening. So at 0 degrees Celsius for water, you have basically liquid water and ice happening, like ice crystals, exactly at 0 degrees. Again, it's not until you get a little above 0 degrees that you fully go into liquid water, or less than 0 degrees that you go into ice. But exactly at 0 degrees, you have both. There is probably, not surprisingly enough, energy required to do that transition in both directions, and that is what is referred to as the delta H of fusion, or the heat of fusion. And the heat of fusion is that energy that's required to, again, do nothing more than take a substance from solid to liquid, or from liquid to solid, not changing the temperature. Again, this all occurs at the same temperature. Again, for water, it's roughly 6.02 kilojoules per mole, are about 335 joules per gram. It's the same idea as we go from solid to liquid. That's a positive 6.02 kilojoules, as it's an endothermic process. As you go from liquid back to solid, it's a negative 6.02 kilojoules, as that is an exothermic process. It has to release that energy as you do that. Any questions on that there? Now, to get water at 0 degrees to turn to ice, we do have to release that heat and energy. And to get liquid water to form at 0 degrees, we do have to apply energy. So as we release energy with ice, um, we get the hydrogen bond in water, and because they lack that much energy, that is where we create these big holes, if you will, or empty spaces between the water molecules as it starts to freeze. And again, that's why ice has a lower density than liquid water, because it creates all that empty space between the water molecules. It kind of balloons up the volume. And when you have a larger volume, you're going to have a smaller density than, say, in liquid water. And liquid water still has enough energy to kind of get closer than they can to each other, because they still have that little bit of energy. Heat transfers right from hot to cold, right? That is why when you take your ice tray, you fill it up with water and you put it into the freezer, the water's temperature is actually hotter than the freezer's temperature at that point, and that means all the energy from your room temperature water will exit, and that's going to create ice at that point, right? When you put it in there to make ice cubes and stuff like that in that particular situation. Now, sublimation and deposition are two of the other sort of transitions that occur. And sublimation is the transition that takes you directly from solid to gas, again, skipping the liquid stopover. And deposition is heading in the opposite way there, going from gas back to solid, also skipping the liquid part of that. Here in sublimation, it is an endothermic process. Again, I got to put heat and energy in there. So a common example, again, of something that can do sublimation is dry ice. And dry ice is really not water, but it's actually carbon dioxide. And dry ice, if you've used it before, goes directly from solid all the way to gas. No liquid cleanup as it melts away or sublimates away. And going from gas back to solid, for example, DVDs, CDs, shiny little things like that. That's how they become shiny. They go through deposition. They drop on metals on the surface of DVDs and CDs, if you could still find those things somewhere. And that's how they get really, really shiny and stuff like that. There's also a heat of sublimation and heat of deposition. That's basically, since we're going directly from solid all the way to gas, that's basically your heat of fusion and heat of vaporization together, right? It's going to take you all the way from solid to gas. Now, as I mentioned before, that energy to change state is that molar heat of fusion and the heat of vaporization. We're not going to do too much calculations involving these, since technically in the next class we do this chapter, the heat energy chapter that they moved out of here. But, if you want to know, for example, how much energy would be required to melt, 75 grams of ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. You could use the heat of fusion, which is the energy required to do that. And you simply can take 75 grams of ice, times it by the heat of fusion, which is 335 joules per gram for water. The grams will cancel out. Ouch. And what we will see is 75 times 335, about 25,125 joules of energy is required to be put in to melt that 75 grams of ice. Now, if I wanted to go backwards and I wanted to go not from solid to liquid, but I want to go from liquid back to solid in this case, the calculation would actually be the exact same calculation. It would be 75 grams of my liquid water. But this is an exothermic process, so it'll be negative 335 joules per gram. And that will give me negative 25,125 joules. So it is the same amount of energy to go either way, just the sign is different to indicate whether it is exothermic or an endothermic process happening. Now, as comparison, for our heat of vaporization, it actually takes a lot more energy to do that transition as you go from liquid to gas than it does as you go from solid to liquid. And the reason why it takes a lot more energy to do that transition is as you go from liquid to gas, everybody's completely breaking apart from one another, which means it's going to take a lot more energy to get everybody into the gas phase. And as you go from solid to liquid, they are moving apart from each other, but they're still relatively close to one another. So they're not completely breaking apart from each other. So it takes a lot less energy. So just to show you that, if you did the same calculation and you had 75 grams of water and you want to know how much to go from liquid water to gas or steam at 100 degrees Celsius, you would use the heat of vaporization for water, which is 2260 joules per gram. And to take that same 75 grams of liquid water and now try to get it into the gas phase, it's going to take you about 169,500 joules, a significantly much more energy to do that transition than to do, obviously, the previous one there where we're going from solid to liquid. Obviously, if you're going from gas back to liquid, the same calculation set negative, and you would end up with negative 169,500. So it always takes a lot more energy to do that transition at the boiling point than it does at the melting point. Any questions on that there? Now, as you'll learn in the next class, you take this with that specific heat equation. You could figure out, for example, how much energy it takes to take ice from like -2 degrees all the way to like steam at like 120 degrees. And you could do all the steps along the way. But I guess we'll save that for 200B, I suppose, if you're taking it. All right, so that is a heating cooling curve, and that's basically what we've been talking about. So this is ice, which is basically solid water, obviously liquid water, and steam is obviously the gas version. So this is 100 degrees Celsius right here, which is the normal boiling point for water, and that is where we use our delta H of vaporization to do that transition. And you can see here it's much smaller down here at our melting point for water, and that is where we would use our delta H of fusion. Again, anywhere on this graph where it kind of goes upwards, that's all the same phase, but the temperature changes. So that's all the same phase, but the temperature changes. And once again, if you had to do a calculation for that, that would be your specific heat equation if you had to do some type of calculation involving those areas. All right. All right, so the next thing we're going to talk about is, since we're talking about phase changes, we're going to talk about what are referred to as phase diagrams. And phase diagrams basically allow you to look at a particular substance and make some predictions as to, for example, if you did want it to boil, what kind of pressure temperature relationship would you need for that to occur? Or if you knew a temperature pressure sort of combination for a particular substance, you could use a phase diagram to figure out what state that compound would be in. So a phase diagram has the three phases, and by the way, the three phases are solid, liquid, and gas. Yeah, and the six inner conversions between them. What are the six inner conversions? It's the ones we just went over. That is melting, that is freezing, that is evaporation or vaporization, that is condensation, and that is sublimation and deposition. So these are the six conversions that occur. So these phase diagrams have temperature, pressure values associated with all these things. When you look at a phase diagram, there's a particular point on the phase diagram, which is sometimes referred to as the triple point. And the triple point is basically the pressure temperature combination that you need for that substance to have all three phases happening at the same time. So to have that substance be both in solid, liquid, and gas all at the same time. And there's a certain sort of pressure temperature relationship that does that. Water's phase diagram is a little unusual. It has sort of a unusual melting point line and a negative slope. And again, that's a result of ice being less dense than liquid water. So if we look at a few more important parts on a phase diagram, and we'll take a look at one in just a second, but there is what is referred to as the critical temperature. And the critical temperature is the temperature where there really is no distinction between the liquid and really the gas phase. So it's that temperature where if you hit it, it just all kind of flows together. So you got some properties of that compound at that point that's very much like a liquid, and you have some that are very much like a gas. Along with the critical temperature, there's that critical pressure that usually goes with it. And that is the pressure where, again, if you go above it, there's really no distinction between the liquid or the gas phase. And if you're at that point, sometimes you'll see the graph and it'll be like this point right about there. And that is sometimes what is referred to just generically as the critical point, which is the critical temperature and pressure relationship, where above that, it flows from, say, liquid into the gas phase, and there is kind of no distinction. And at that point, that is what is referred to as a supercritical fluid. That is one where it is above really the critical point, and it has a density that's similar to a liquid, but it will flow like a gas. So if you're kind of above that temperature pressure combination, you'll have what is referred to as a supercritical fluid. And again, it kind of flows like a gas, but has a density similar to a liquid. So here is a generic phase diagram, and you do need to know where everything is on this diagram. So here, typically we go solid, liquid, and gas. So kind of left to right in those different quadrants, solid, liquid, and gas. As we go across the melting point curve here, we go from solid to liquid, that is melting. And if we go in the opposite direction, liquid back to solid, that is freezing. This is our vapor pressure curve. And as we go from liquid to gas, that is vaporization. And as we go from gas back to liquid, that is condensation. Down here, this is solid, this is gas that does not pass through any liquid part there. And that is where sublimation occurs and deposition occurs, depending on which way you're going. There is, again, no passage through the liquid portion of the graph at that point. Right here, where all the phases come together, that is our triple point, and that is the pressure-temperature relationship where all three phases are happening at the same time, solid, liquid, and gas, basically. How would I know where my normal boiling point, melting point, freezing points would be? Standard pressure is 1 atmosphere. So if you find 1 atmosphere on your graph and just draw a straight old line straight through that, right there is our melting point or freezing point, that temperature, whatever that temperature would be. And right about there would be where our boiling point temperature would be in this made up one. By the way, if you find yourself right on the line between solid and liquid, the phases that are occurring are both solid and liquid. It's happening at the same time. So you're right on that transition point. If you find yourself directly on one of those lines, like this guy over here on the right, would be liquid and gas basically happening. This is our critical point over here. That's where our critical pressure would be if I drew a straight line, and our critical temperature if I drew a straight line down. And above that is where you find your supercritical fluid. As you can see, that's kind of the open space between liquid into really gas as it flows kind of from left to right there. So again, it has sort of properties of both. There's no sharp distinction between those two different phases. Any questions on that there? Yeah. You might, yeah. So you might need to know where everything's sort of located. Yeah. Other questions? So if we take a look at carbon dioxide here, this is dry ice basically, and this is the phase diagram for it. And again, here is the triple point. So that is where we would find all three phases happening for carbon dioxide. Now, under normal conditions, pressure is about 1 atmosphere, which if we follow what's going on here, that is 1 atmosphere. And if I go straight across, I went from solid directly into gas. It goes through sublimation under normal pressures. That's why dry ice just goes from solid directly to gas. It does not hit the liquid phase. If I wanted to force my dry ice to go into the liquid phase, I would definitely need to get a pressure that is greater than 5.1, right? It has to be up here. And I would definitely need a temperature that is probably past this point. So I definitely need a pressure temperature combination here to get that dry ice to actually go into the liquid phase. So that's 5.1, which is 5 times greater than normal pressure. And probably where I drew my thing, since it's not perfectly scaled, is quite high. Probably it's about 30, 40-ish in terms of atmospheres, which is like 40 times normal pressure. So you can see why under normal conditions, you never find dry ice basically making a liquid mess. You would need an incredible amount of pressure to force it into the liquid phase to do that, and also the temperature. Most of the time we're at 1 atmosphere and, dare I say, 25 degrees, which means if you just leave it out, it's going to end up in the gas phase. And that's why, again, it just goes directly from the solid to the gas. Any questions on that there? All right, so why don't you take a moment here, and for each of these sort of conditions, decide what phase or phases this CO2 would be in. So that's solid, liquid, and then. Okay, so let's take a look. So if we look at the first sort of conditions, we have a temperature at 20 degrees and a pressure at 72.9. So that's that line up there on top. The other line on the bottom is 31 coming up to that point, so 20 would have to be back a little bit. So that would put us probably here in the liquid phase in this case. If we look at the next set of conditions, we have a temperature of minus 56.7, which is right about there. And we have a pressure of 5.1, which puts us right there. And that is at the triple point. And at the triple point, you have all phases happening at once. So you would have solid, liquid, and gas basically all occurring at the same time. So if you want everything to occur at the same time, you got to take your dry ice to about 5 times normal pressure and drop the temperature to negative 56.7. You'll have everything happening at once. I don't know how happy you'll be standing in a room like that, but you would have everything happening. Here at 10 degrees Celsius, which I don't know, is somewhere in this region-ish, and 1 atmosphere, which would be here. So if we come across, we're somewhere here, and that would put us in the gas phase at that point. And if we come over here at minus 78.5, which is down here, and 1 atmosphere puts us actually right there on the line, and that is the line between solid and gas, basically, which means we're at that transition between solid and gas sublimation, and we actually would have both phases occurring since we're right on the line and would be in an equilibrium with both of them. Lastly, we have 50 and 80 atmospheres. So 80 is definitely above this number, and 50 is definitely past this number, which means that puts us right there above the critical point, the critical temperature and pressure. And above that, you have that supercritical fluid basically happening at this point. Any questions on how to use a phase diagram to identify what things are or where they're at? Again, as I mentioned before in that sort of last slide, you could also use these phase diagrams to figure out, like I said, what pressure you might need or temperature you might need to maybe force something to go through a liquid phase or a gas phase or a solid phase. Any questions on that there? That's nice getting. So let's talk a little bit about water, just a few more parts about it. Water is obviously important in life. It has the largest thermal conductivity and highest surface tension because of its hydrogen bonding. And again, as we talked about, very unusual for a substance that in its solid phase, it has a much lower density than, say, in its liquid phase. And again, that is a result of it slowing down as it goes into ice. It also, again, hydrogen bonding, so it doesn't allow everybody to get as close as they can, like they could actually do in the liquid phase where they have a little bit more energy, so they're able to kind of move around a little bit more than in the water or ice phase. So because of that hydrogen bonding, we do get the opposite attraction between different water molecules. So they do hydrogen bond through, for example, the hydrogen of one and the oxygen of the other, as the oxygen is more negative, hydrogen side of water is more positive, and that's what creates the hydrogen bonding that occurs in water. There we go. Now, water molecules in ice, again, tend to expand because of that. And again, if you've ever put like a soda can in the freezer and forgot about it, and you come back later, the bottom of it is bulging, right? And that's because as those water molecules in the soda starts to freeze, it has no room to go, so it expands your aluminum can as best as it can, right? Or if you're in a glass jar, it will break it at some point, perhaps, because the glass is going to give, right? And you take your soda can out and you put it on the table, it just wobbles around a little bit as you go look at it. And again, that is from their bigger empty volume through the hydrogen bonding, not allowing them to get as close to one another. Now, all phases of matter, with a few exceptions, tend to expand when they're heated. Liquid water actually below 40 degrees, or 4 degrees Celsius, not 40, is bloated with ice crystals. And when it warms from 0 to 4 degrees Celsius, the volume does decrease. and they start to have a greater density. So the greatest density of water is 1 gram per milliliter, which we typically use in most situations, but density does change with temperature. So as you looked up, I think the other day there in that experiment, based on temperature, you have different densities that occurs. And that's really good in the sense for water, because water actually freezes top down rather than from the bottom up. And that's good for everything that lives in water, because if it froze from the bottom up, there'd be a lot of frozen things living in water, maybe not living so long. So what actually ends up happening is the warmer water is going to be greater density. So it actually will drop to the bottom. The colder water will actually float to the surface. And what ends up happening is, in this situation, we have the warmer water coming down because it's more dense. The cooler water actually goes upwards because it is less dense. When it reaches the top, it starts to freeze and actually creates an insulation that occurs here. It actually protects the rest of the liquid water down there from freezing. Although my friend here, Melvin, which is his name, by the way, that is Melvin the fish. Although he does look like he's in an ice cube, he's not. He's just floating around in there and stuff. He's happy and moving around. You never know. His name might pop up on the next exam, so make sure you know it. But that it allows obviously everybody in like lakes and water that fishes and life to still move around. The only way you could get to them at that point, right, is to cut a hole and then do ice fishing. No, don't do ice fishing, right? Also, why you don't walk on a lake, right? So it just froze. Because although it looks icy to you, right, and it's iced, it may not be that iced, right? And you actually crack through it because there's water underneath there. And then you'd be very cold with Melvin down there as you're swimming around. All right, so any questions on liquids there? We're now going to talk a little bit about solids and some different types of solids and some interesting calculations involving solids, I suppose. So solids are rigid, and again, they cannot transmit pressure in all directions. There are a couple of different types of solids. There's crystalline solids, which are very ordered sort of arrangement. They have long range sort of orderedness in terms of how they come together. So when they come together in a nice solid form, they are very much organized. And things like ionic compounds, like salts, minerals, are examples of that. Amorphous solids exhibit very little long range order, and they don't have a definite shape. And they are still hard, but things like glass, for example, organic polymers, are amorphous type of solids. So when a solid is allowed to cool, it will actually create a crystal lattice. And the result of this crystal lattice is a very organized way and a lot of crystalline solids that creates a very repeatable pattern. And it's such a repeatable pattern that if you just sample just a little portion of it, all you need is that little portion, and then you could actually rebuild the entire structure of, say, that crystal. So, for example, if we had some atoms in a solid sort of structure here, and we wanted to sort of sample this and create what's known as a unit cell, which is this sort of repeatable unit of this solid. Now, you might think to yourself, well, maybe I should just grab, an entire molecule. That would be good. The problem with doing that is if you take just that entire molecule, you don't really know where to put it. There's no relationship to its neighbors, right? And how it attaches or is arranged in terms of its neighbors. So when you're kind of selecting a unit cell, you wouldn't want to select necessarily just a whole sort of unit. Perhaps what you would want to do is sample a little bit from each of some different molecules. And if you pull this unit cell out, what you'll end up with is something that looks like this. Now, although you don't maybe have a whole atom in that unit cell, you now have a pretty clear understanding of how you should arrange it, because now all you have to do is take that unit cell and basically just start stacking it on top of each other. And if you do that, you pop one above it to match up our half a circles there. You pop one to the side, which matches our circles over here. Put one over here. Now, before you know, if you just continue that pattern, you have now rebuilt basically your entire sort of three-dimensional structure. So when choosing sort of a unit cell, what you're looking for is not just one atom or the entire atom, but you're also looking for its relationship to its neighbors so that you have that sort of order as to how everybody comes together. And that's what we see down here. Unit cells are three-dimensional. They contain different layers, and if they are repeated over a long period of time, you can reconstruct your sort of uh, molecule here. Here they chose one that does have a whole molecule in the middle, but it still has the relationship here on the corners of how that guy is related and positioned to everybody else. So that allows it to be used to reconstruct the entire sort of three-dimensional arrangement. Now, there's different types of unit cells. There's cubic, tetragonal, a whole bunch of them. We're just going to focus on the simple ones, which are cubic, which they all have 90 degrees because they're cubes. And also because they're mainly cubes, the volume of these guys is the length cubed, right? Like we do centimeters cubed as a volume, right? So same idea there is how we can do that. So let's talk a little bit about these unit cells. The number of particles that come in contact with one another, that is what is referred to as a coordination number. And the higher the coordination number, that means there's more interactions between the different atoms, and there's a stronger attractive force, and that crystal is going to be held tighter than one where there's less sort of interactions between molecules. We also have what is sometimes referred to as packing efficiency, and that is the percentage of how well all those molecules can occupy the same space. Now, when we talk about cubic unit cells, as I mentioned before, the volume of a cube is the length cubed. So you can take the length cubed. The volume of a sphere is 4/3 pi r cubed. Most of the time in here, we will just be using the length cubed to figure out our volume. And they all have 90 degrees. The lengths of all the edges are equal to each other. And when we talk about a unit cell that's made up of spherical particles, like circles, if you will, if you have a part of a particle or a molecule in a quarter, that's 1/8 of an atom. If you have one that's cut right in half on the face of the cube, that's a half of atom that's there. And you have 1/4 of an atom if it's within the edge or on the edge of a cube. These are the three types of cubic cells, unit cells that we're going to talk about. One is simple cubic, is sometimes abbreviated as just SC. This is body-centered cubic, which is sometimes abbreviated as BCC. And this last one is face-centered, which is FCC, sometimes abbreviated. Now, there are a couple important things that you need to know about these things. And the first one is how many atoms there are per unit cell. So if you have something that is simple cubic, you have just one atom that makes up that unit cell. If you have a body-centered one, you have basically two total atoms, and we'll talk about where they are in just a second. And if you have a face-centered, it will actually have 4 atoms involved in that unit cell. You could also calculate the length of the edge or the edge length using these formulas here. For a simple cubic, it is 2 times the radius. For a body-centered, it is 4 times the radius divided by the square root of 3. And for our face-centered, it doesn't look like it there, but it's actually 2 times the radius times the square root of 2 is basically what it is. It kind of looks like this R is underneath it, but it's not. So that is what you need here. You can see with face-centered, there's much better packing efficiency because there's a lot more atoms basically in contact with each other in this particular case. So let's take a look at each of these individually and talk about where we get all those atoms from and all that kind of stuff. So the first one is our simple cubic. And in a simple cubic, we basically have 1/8 of an atom in each of the corners of this unit cell. So if you pulled out this sort of cube, you would have 1/8 of an atom in each of the corners. Since there are 8 corners within a cube here, 8 times 1/8 is 1 atom, basically. So you have basically 1 full atom as a result of 1/8 of an atom stuck in each of these corners, basically here. The length of the unit cell is 2 times the radius, and that's how you would calculate the length. So important to know for simple cubic, it has 1 atom, and the length is 2 times the radius, basically. Now, if we look at this here, you can see they kind of slice here 1/8 of these atoms in each of these corners, and that is what we kind of see down here. Come here. There we go. This sort of 1/8 of an atom in each of these corners. Now, the next type of cubic cell, as I mentioned, is a body-centered cubic cell. And in a body-centered cubic cell, also abbreviated BCC, you still have the 1/8 of an atom in each of the corners, which is going to give us our 8 times 1/8, which is 1 atom. Now, because this is body-centered, you also have one entire whole intact molecule sitting right in the center of the cube. So that is plus the 1 in the center, basically. And that gives you a grand total of 2 atoms that are occurring in this type of unit cell. To calculate the radius or the length of our cell, it is 4 times the radius divided by the square root of 3. So this type of body-centered cubic cell has 2 atoms, and that's how you calculate it. And it does depend on the substance you're talking about as to how it will crystallize. And usually in the problems, it'll say, hey, this thing crystallized in a body-centered type cube, or this crystallized in a simple cubic unit cell. And that is the key to know, again, how many atoms you're dealing with and how to calculate the length. Here you have a lot more sort of coordination as everybody's in a lot more contact because there's more atoms involved, especially with it being in the middle. It's going to come in contact with those guys on the corners and all that. So it's going to give you a greater coordination number in this particular case. The last type of unit cell is a face-centered, which again is FCC here, abbreviated. And in this one, what we have going on is a couple of things. We actually still have in each of the corners our 1/8 of an atom basically happening. So just like in all the others, we have basically 1 atom that's made up of all the corners of this cell. Different on this one is it actually has an atom that is being dissected right on the face of the cell, of the cube. And it basically will cut that atom right in half. So you basically have 6 faces on a cube, right? So you have 6 sides to a cube. And you have an atom that's basically being chopped right in half, like it goes right through the half of it. So that gives us 6 times a half, which gives us 3 more atoms involved. And that gives us a total of 4 atoms that are happening here. As you can see here, you have an atom stuck right in the face of each of these guys. And again, it pretty much will dissect that atom right in half. And you'll have a half an atom on each of those faces. To calculate the length, it will be 2 times the radius times the square root of 2 in this case. And that's what you can see here. It's dissecting basically those atoms on the face right in half. So you end up with just a half an atom that's left on that particular unit cell. Because of the lot more atoms involved in this particular unit cell, you're going to have a greater coordination number. Things are going to be in contact with each other a lot more than it will in the other 2 forms. As you can see there, again, it will slice those guys on the face right in half. You have your 1/8 of an atom in each of the corners. And again, and all together, that will give you your 4 total atoms. So for face center, 4 atoms. body center 2 atoms, and simple cubic 1 atom. And that's going to be really important for the calculations, which we will